Good day, students. The topic we're having today is energy of simple harmonic motion. Now, as we see that we have a pendulum that swings to the left and to the right. And when you swing to the extreme end of the right hand side, when it's at rest, potential energy is mgh, that is energy at rest. M is mass, G acceleration due to gravity, H is the height. But at this extreme end, when the box swing to the last point of rest, potential energy is at maximum, is energy at rest. But velocity of motion, when it's at rest, before moving backward, V is zero because it's at rest. Kinetic energy is zero. You know, when velocity is zero, kinetic energy returns to be zero. Return everything to zero. And at the middle, when the pendulum ball comes and gets to the middle, the height is zero. When the height is at zero, the potential energy will be zero. Kinetic energy is half mv squared, and kinetic energy is maximum at this point because it's moving at a faster rate. Velocity is at maximum at this point. We make kinetic energy to be maximum at the middle. At the extreme end, what is applicable at the right hand side is applicable at the left hand side. Potential energy is at maximum concentration between the two motions. But at the middle, height is at zero. It's not due to concentration. We assume that the kinetic energy is at maximum. Now let's see the linear velocity v at any point q, here, at any point q, whose distance from C is called the linear velocity v at any point q, whether it moves here, it moves here, it moves here, at any point, at any point q, whose distance from C, whose distance from this C, the central point, is x. Take note from between C and Q is x. Is given by V equals to W, which is angular speed, square root of a squared minus x squared. Take note of this formula, is very important. V equals to W square root a squared minus x squared. A squared minus x squared. The maximum velocity Vm corresponds to the velocity at x is at zero. When x is at zero, that means that the distance here will not be put into consideration. The maximum. The example is when you are swinging your hand like this, the middle at the center of your hand here, there's maximum rotation. Before your fingers move around the circle, your shoulder has already moved at maximum. The same thing here. The maximum velocity Vm corresponds to the velocity at x equals 0. At the middle, we experience maximum velocity before the point P. This middle, the point at the middle will have moved around the circle. It moved faster before the one at the circumference. That's why when you see someone running a relay race, someone close to the middle of the circle, if he can run very fast, he will complete a circle before the one at the extreme end. That's what we mean that the maximum velocity Vm corresponds to the velocity at x equal to 0. When x is 0, you have the maximum velocity here. And that is the velocity at the central point or central motion, Vm, velocity at the maximum, equals to W, angular velocity, square root a squared minus 0 squared. The 0 is taken as 0 because we assume it's at maximum. 2 cancels to the square root, we have Vm equals to Wa. Take note at when you have to calculate maximum velocity, linear velocity, you make use of Wa. When the motion of an object is simple harmonic motion, there is always a restoring force tending to restore the body to a central or equilibrium position. Since force and displacement are involved, it follows that work and energy are involved. Take note, since force and displacement are involved, follows that work and energy. Work is force and distance. Energy also, when there's work, energy will be involved, which is when work is involved, energy is involved. Since we have force and displacement, force will move the object toward the right or toward the left, and there's a displacement of the object. Due to that, work and energy are involved in the motion. The subheading we are having under energy of simple harmonic motion is energy transformation of a simple pendulum. The total energy, kinetic energy plus potential energy for such a body performing simple harmonic motion is always conserved, although it may change from potential energy and kinetic energy. When it swings to the left, that's potential energy to the extreme end, and potential energy is at maximum because it rests. And there is h given, there is height to which it moves. When it gets to the middle, there is no height. When it moves to the right, again, or to the left, there is between the middle, when there is maximum velocity and we have maximum kinetic energy. When it moves to the left or to the right, height is taken into consideration, but when it's at the middle, it's only velocity that is at maximum. That's what you are saying, that it changes, although it may change from between potential energy and kinetic energy. For a simple pendulum, the energy at the extreme position, as I said before, R, between position R at the extreme end and Q is always potential energy and is equals to mgh, energy at rest. M is mass of the object or the ball, G is associated to gravity, H is the height when it moves up. At C, that at the middle, H equals to 0, potential energy is 0, but it will turn other ones to be 0. But velocity Vm of the moving ball is maximum. Hence, kinetic energy is maximum and equals to half mvm squared at C. You have to put m there at the middle because velocity is at maximum at the middle point, at the center of motion of the pendulum. Now, from the conservation of energy principle, the total energy in the system will be constant. Therefore, maximum potential energy equals to maximum kinetic energy. Potential energy plus kinetic energy at any instant. Because when it's at the middle, like maximum kinetic energy, as it's moving, it's trying to move from potential energy to kinetic energy, potential to kinetic energy. That's what I say, that maximum potential energy equals to maximum kinetic energy equals to potential energy plus kinetic energy at any instant. Now, since it's like that, now mgh equals to half mv squared. You equate the two together. In that case, for the same mass of the ball that is moving, m cancel m, that's why it remains constant. Gh equals v 1 times vm squared over 2. You cross multiply, you have vm squared equals to 2gh. Find the square root of both sides. So you cancel the square root. V maximum equals to square root of 2gh. When you are given center of gravity and h, you can still make use of Vm. Therefore, maximum velocity equals square root of 2gh. During the motions of the ball, the force tending to restore the spring to its equilibrium position is called elastic restoring force, F, is equals to minus ky. Minus ky, minus is just saying that opposite tend to restore it. When it's moving sideways, it falls in opposite direction. We are not going to make use of it in the calculation. Just know that we are dealing with ky. F equals to ky, that's elastic restoring force. Y is the distance of the elasticity. When you strain the string, the distance of the elasticity, when it gets elastic, become elastic because of stretching. Now, just know that force equals to ky, elastic restoring force, or restore it back to its normal position. Where k is the force constant of the spring, the total work done, W, done in stretching the spring a distance y. That's what average force times distance. I told you that the force, restoring force, elastic restoring force is ky. But when you have to look for the work done, you know before that work done is force than distance. But we are looking for the average force. But we have several forces being applied before we stretch the string. But we have to look for average force, not ordinary force, average force. And when you are looking for average of a force of two things, let's assume that it was stretch and stretch again. The half of 2 times of stretching is 1/2. Now make it of half ky times y, which is the distance. Half ky first, the distance also is y. You know that that's the distance stretching. But when you go for the half of this, now multiply by the distance. Now half ky squared. Always know that the work done in stretching the spring is half ky squared, and also elastic restoring force F equals to minus ky. Thus, the maximum total energy stored in the spring, equals half Ka squared. Take note, if you have to look for the maximum total energy stored in the string, then equals half Ka squared. Now, where A is the amplitude of the motion, at any stage of the oscillation, the total energy that we have is half Ka squared equals half mv squared plus half Ky squared. The addition of the kinetic energy with the potential energy will give us the maximum energy stored in the string, half Ka squared. Now we want to look for the velocity. Take note, look at the way I want to do my mathematical analysis. Half Ka squared minus half Ky squared equals half mv squared. We are looking for v squared. What we do is that we factorize half k open bracket a squared minus y squared close the bracket equals half mv squared. Now from here, what do we have to do? We cancel the half, Now k bracket a squared minus y squared equals mv squared. Divide both sides by m. Well, we're making v the subject of the formula. M cancel m. We have k over m a squared minus y squared equals v squared. From here, we find the square root of both sides. To cancel the square root, you have v equals the square root of k over m into a squared minus y squared. You can separate it because square root of k over m, square root of a squared minus y squared. If a is the amplitude, k is the elastic constant. And from there, you should know that the constant k is obtained. The constant k is obtained from Hooke's law. The constant k is obtained from Hooke's law. It's obtained from Hooke's law, in which we have F equals to mg, because mg equals to ke. Is Hooke's law formula, where is the extension produced in the spring by mass of F. Where E the extension produced in the spring by the mass M. Take note. But in our previous derivation, we have V, don't forget to be W, square root of A squared minus X squared. In our previous explanation. Now, based on what we have here, our W equals square root of K over m. We know that one to be square root of k over m. Hence, still remember that we have w equal to 2 pi f. But this our f can become 2 pi over t. Now, you can now have cross multiply. When you have w equals to 2 pi over t, now t can be equals to 2 pi over w, which is equals 2 pi over, you can write it square root of k or square root of f, which is equals to 2 pi over 1. This one is together, divided by square root of k over square root of m, which is equals to 2 pi over 1 times, change the notation, square root of m over square root of k, which is equals to 2 pi square root of m over k. Okay, let's take note that we can look for our period to be equals to, therefore, period t equals to 2 pi square root of m over k. Take note. Based on our derivation, our t, the period, equals to 2 pi square root m over k. The period t, therefore, depends only on the mass m and the force or elastic constant. Mass m, force or elastic constant, called k, force or elastic constant. It does not depend on the amplitude of motion or on the value of g at the point. In actual fact, the spring has a mass m, m0, hence the value, the true value of the period t equals to 2 pi square root of m plus m0 over k. This is the end of our class. In the next class, we're going to some calculations under simple harmonic motion. Have a nice day. Thanks.